Друзья, наш сегодняшний выступающий Боб Гринье появился. Я буду говорить по-русски, потому что знаю, что у него есть Google переводчик, поэтому он, в общем-то, понимает, о чем я тут говорю. Вот. И поэтому буду в основном говорить по-русски, но с ним буду иногда говорить по-английски. Сегодня, но презентацию он будет давать по-английски. Итак, я включил видео и прошу всех, кроме ведущего Зателепина Валерия и выступающего Боба Гринье, всех отключить микрофоны. Вы будете все слышать, но ваши звуки не будут мешать проведению нашего вебинара. Жак, I ask you to switch off your microphone. Анатолий Климов, I ask you to switch off. Надеждин, Никитин, thank you very much. Thank you very much. Фомин вот не понимает, что надо выключать. Так, и почему-то и Боб Гринье выключил, но он включит, когда будет выступать. Итак, я включил запись, это означает, что мы начали формальную часть нашего вебинара номер 10, сессии осень-зима 2021. Вебинар номер 10. Сегодня 8 декабря 2021 года. Московское время 16 часов 5 минут. Мы немного задержались по отношению к нашему стандартному времени, но ничего страшного. Сегодня доклад Боба Гринье «LENR in a can». Ну, там еще есть некоторое объяснение, что имеется в виду. Ну, я хочу несколько слов сказать об этом докладе. Ну, во-первых, can – это по-английски банка, вот банка из-под пива, то есть LENR в каком-то маленьком объеме. Вот о чем идет речь, то есть удобные для использования. И об этом сегодня будет говорить Боб Гринье. Но основная, конечно, его цель – это не энергия, цель его доклада, и это очень правильно, на мой взгляд, а показать многочисленные изменения элементного состава, которые происходят в окрестности материалов, которые находятся под действием омаса газа. Несколько слов о том, что такое омаса газ. Вот мне звонили люди, спрашивали, что это такое. В принципе, можно посмотреть в интернете, что это такое, но я все-таки тут пару слов скажу, для того, чтобы сразу аудитория могла включиться вот в ясное понимание того, что сегодня будет рассказываться. Омаса газ, с понятием омаса газ, вот я лично познакомился где-то примерно полгода назад от Анатолия Ивановича Климова, который эту идею принес. По-моему, она у него возникла при общении со Слободаном Станковичем, на которого сегодня будет ссылаться и кое-что говорить о нем будет Боб Гринье. Возможно, даже мы вот Станковича сюда сможем и пригласить с помощью Анатолия Ивановича Климова, при помощи общения вот того, которое они имеют. Пару слов все-таки, что это такое. Это электролиз воды, то есть подключение электродов к некоторому напряжению, электродов, погруженных в воду. Но это не просто электролиз, а электролиз, при котором сам объем вот этот водяной, он очень сильно перемешивается разными способами, и в частности Омаса. Омаса – это фамилия изобретателя вот этого метода, это японец. Перемешивание осуществляется с помощью вибрации вот объема, в котором происходит электролиз. При этом, как утверждает Омаса и его команда, образующийся водород и кислород не перемешиваются, как это происходит обычно вот при электролизе образуется так называемый гремучий газ, а образуется такая вот смесь, которая даже может сжиматься, например, в двигателях, и они такой двигатель, похоже, уже разрабатывают. Кроме того, этот газ может использоваться в горелках. То есть это такое соединение пузырьков в воде очень сильно перемешанных и очень малого размера наночастички этого газа, газ-водород, газ-кислород, и это не смешанные два небольших объема, один заполнен водородом, один кислородом. Такая модель у Омаса. Есть другие модели, объясняющие это явление, очень интересное. Я сейчас не буду их касаться, потому что и так мы уже затянули на начало нашего вебинара. Я лишь только скажу, что вот Слободан Станкович, он внес, по-видимому, он внес в нашу вот комьюнити, исследующую LENR, идею о том, что вот такой газ может быть Боб, I finalized my presentation. It give you possibility to switch on your screen. I give you permission, and I finalized my introduction. И вот, значит, Слободан Станкович, он предполагает, ну, возможно, не только он, предполагает, что вот этот Омаса-газ в первую очередь состоит и важен не столько из-за того, что там какое-то разделение водорода и кислорода, а из-за того, что там имеется вот объединение протона, по сути дела, это ионизованный водород и гидроксила, и отрицательно заряженного гидроксила, и вот это взаимодействие такое своеобразное, вот это есть основа процессов, которые там происходят. Но у Боба Гринье свой подход к этому, он сегодня о нем расскажет. Я закончил свое введение. Боб, your floor, please. Bob, switch on your microphone. Turn on your microphone.
Okay.
Bob, once again, wanted to remind you, don't hurry, slow, separately words for better understanding. More few words, more sense. It's my request for you. Thank you.
Okay, so thank you very much, Valery Zatelepin, for inviting me to make this talk today, and to the Russian community for taking the time to listen. I would also like to thank Anatoly Klimov's interest and Irina Savatomova, who have shared their works with me over the years and recently. So thank you to those scientists. So what I have for you today is LENR in a can, and I believe that this is near instant transmutation, and I'm going to give an example of tungsten and other materials using Омаса gas. So before I go into the main presentation, I'm going to give a bit of background. Much of this you will know, but my personal phenomenological hypothesis is that whatever is going on in cold nuclear transmutation is a process that likes to fit things into a small box. And so therefore energetically advantageous products will be favored. And I know many of you have a similar opinion. For me, the statistical guide for products outside of energy yield is crustal abundance, since the driving processes are ubiquitous, being friction, fracture, compression, cavitation, sound, electrical discharge, etc. The process likes to reduce input materials to alpha particles. Products are largely alpha conjugate nuclei, including alphas, with carbon, oxygen, silicon, calcium, etc. very common. Energetic alphas can lead to transmutation, production of protons and tritium due to fermionic nuclei. Other fermionic nuclei, for example, are favored: 23 sodium, 27 aluminium, 61 nickel, 207 lead, as they don't easily fit into the small box condensate. So this is my view. If you push it too far, it will also cause the collapse of baryons in what Matsumoto calls gravity decay, but he's not the only person to have observed something similar. So if we're going to be talking about something that is similar to water gas, which is often called HHO, we should probably give credit to Leclerc and Nanospire. Theirs was an HHO system, effectively, and I don't know if I can get rid of this thing at the top. That would be good if I can. Is it going to? I don't know why I'm getting that at the top. So unfortunately, I've got this thing over the top here. I don't know why it doesn't disappear, but anyway. So he found that in laser and ultrasonic driven cavitation, he could synthesize every element in the periodic table and even some radioactive elements, and that he found that he must first burn the carbon. So any carbon you have synthesized, you must go below 55% carbon, and then you start getting iron and higher elements, and that there was a predominance of alpha isotopes, alpha step isotopes being synthesized. And he observed what we call strange radiation tracks in various experiments in the materials of the reactors and outside of the reactor. A similar person, not so much HHO here, was S.V. Adamenko in Ukraine at the Proton 21 labs. And by using a 300 joule discharge into a target metal, regardless of the target, he was able to synthesize nearly every element in the periodic table. Langmuir probably was the first to observe tungsten being fissioned, and this was from around about 1909. And one of the speculations was that there was some water left in the vacuum system or permeating through the glass, and that this would go onto the hot tungsten filament, and that this would produce a volatile oxide of tungsten and produce hydrogen in the atomic form. And I would extend that to say that this then leads to the fissioning of the tungsten filament, and effectively we are talking about HHO here. In the case of Wendt and Irion, they are exploding tungsten foils, and one could not argue that there was HHO involved here, but there is something akin to an extreme discharge of electricity into the metal sample, which is causing the collapse of the matter or the forced decay of the matter. In their work, they say they positively identified the strong yellow line of helium. The appearance of helium and the absence of hydrogen is interesting for two reasons. In the first place, it seems to dispose of the objection that helium arose from gas remaining in the wire. For in the case, hydrogen should also have been visible, for it was probably originally present in the wire in much larger quantity than was helium. In the second place, if the helium does arise from the decomposition of tungsten atoms, the absence of hydrogen is also interesting, because the atomic weight of tungsten is exactly 46 times the atomic weight of helium. Now, I have a note down the bottom because this was prior to the proposing of the neutron by James Chadwick in 1932. So they are just looking at the baryon mass. And Rutherford was also unable to detect hydrogen from the bombardment with alpha rays of carbon, oxygen, magnesium, silicon, and sulfur, whose weights are multiples of 4, though he did detect it with boron, nitrogen, fluorine, sodium, phosphorus, and aluminium, whose weights are not such multiples. An Australian, Simon Brink, has done electrical discharges from capacitor banks into various metals. One of those metals was tungsten, and he was putting water in the gap. So effectively, he would be creating HHO, and he observed a range of elements synthesized, which we typically see, like silicon, calcium, titanium, vanadium, chromium, iron, copper, zinc. Particularly zirconium, I'm just going to focus on here, alongside decreases in the proportion of tungsten. So again, this is effectively HHO. So if you take the exchange reactions here, and this is available at nanosoft.co.nz, where we have created a program which is free to use by anyone, which allows you to investigate the Parkhomov reaction tables with or without cold neutrinos. And you can put in your starting products or target products, and it will calculate the reactions. It's very, very flexible. And we also have a cascade reaction there. So you can have a number of sequential steps. So products can be put it as inputs in. So you can, with this, we have found that it really largely predicts most of the historical data in the field. Anyway, looking at this particular one at the bottom, and I must thank Philip Power in New Zealand for help coding this with me. So if you take the oxygen, which will be in the water, and tungsten 180, I know it's a rare isotope, but that is the most energetic reaction that can come out, and it produces zirconium and molybdenum. The molybdenum will probably go on and fission further, but anyway, this produces 117.485 mega electron volts. And you can't see it's just off the top of the table there, but you will have the charts, the slides at the end of the work here, so you can look at it in your own time. But yeah, so you can see that this is zirconium, and this is the most energetic reaction. So in my phenomenological basis, that is the most likely to occur. Now, if you don't have a very, very small box, then it will do something lower down, or some statistical thing which is based on nature, which could be mirrored in the crustal abundance, would guide what you would expect. But in this case, we do see zirconium, and it's the #1 output from the isotope 180. In the early 2000s, there was a publication by Mizuno et al. I'm not going to go into it, but effectively he had tungsten plus potassium carbonate in water, and it was a discharge. And again, this is HHO. You cannot avoid it. It's going to have HHO in there. And I don't think this has been considered sufficiently. Sorry, I'll kill my phone here. Okay, so you can go and have a look at that presentation. The link is over here, and I analyze that particular data set. So some grounding here, which will probably be less relevant to you guys because you know what I'm referring to here, is this seminal paper, in my view, from Oroitskev et al. And this is the exploding titanium in water. And of course, this will be producing HHO, even if it is really not wanted, it will be produced. And there was transmutation of titanium, mostly 48, to sodium, magnesium, aluminium, silicon, and the other elements there. Ball lightning was produced above, and you can see in the mirror here. Even very weak lines were detected of copper, zinc, chromium, nickel, calcium, and sodium. And so the synthesized material was transported into the ball lightning outside of the reactor. And there was a so-called monopole detection, and Oroitskev subscribes to the Loschak's monopole. He detected it by using iron 57 at 0.7 meters from the explosion chamber, and by using north and south magnets and a control, and looked at the fine constant of the magnetic moment to establish that. And so there's an indication there that they were binding to the iron nucleus and changing that moment. And also he observed what we call strange radiation tracks and the condensed plasmoid. So I think this shows that an intense energy discharge through metal in HHO environment, which will be stimulated at that time, can lead to the production of all these outcomes. And using this thinking, he went on to consider that it was partly responsible for the Chernobyl accident. And the theory surrounding that was that paramagnetic nuclei, and oxygen is, if you look at the paramagnetic nature of elements in the periodic table, I think you have to go up to something like holmium before you get something that's more paramagnetic. It's very paramagnetic, certainly of the most abundant gases in the crust. And so the idea is that it's binding to the nucleus of oxygen, and it's changing its spectral nature. And therefore, if oxygen can accumulate these monopole type structures, whatever they are, then maybe that changes the property of the oxygen such that it can cause clusters of water or water gas that wouldn't ordinarily form without the binding of this material to the oxygen. We must talk, again, another piece of work you will be aware of, which is a water discharge process, plasma flow discharge by Bogdanovich et al. And so plasma flow discharge experiments, he observed the production of spherical and toroidal plasmoids. And so there's one in the picture here. Long-lived plasmoid groups in crystal-like structure, and we'll talk about that in the coming slide. And monopole-like radiation as observed by Alexander Shishkin and Perovskikov, which I'll show in the next slide. In this experiment, there's no screening for north or south magnetic monopoles, and so you get a collection of them. And I think it's highly interesting that Bogdanovich chose to show this particular collection where you have effectively two that are coming to join together, and you have two that are coming to join together here. So one could imagine that one of these is a predominantly north and the other one's a predominantly south or suppressed pole on them. And that's because you have a mix in this instance. Using synchrotron, it fired high energy beams into conversion target, producing gamma and screened out the electrons using a magnet. And you get effectively the north poles going one way and the south poles going the other way. And he suggested that the gamma rays were knocking these structures off the faces of the magnets, which is interesting in its own right. But what I find more interesting is on the one side here, you have two that have been circled and they are joining together, but going in the same direction. So you can imagine that if this was a south and this was a south, they're effectively joining to a degree magnetically. And I think that this is not by accident that he's chosen to circle these two examples in this way. You may also be aware of Perovskikov. You can probably say this much better than I can, his work. And there's been some doubt raised about this, but anyway, the 0.4 Tesla magnets under a Petri dish of water exposed to the sun for a period of days and then exposed to a laser, which obviously has cohering forces in its own right, and then exposed onto standard film. This is a colorized version of Bogdanovich, and this is my sort of animation of what this thing should look like, and it would be if it showed me. Let's try that again. Okay, so there's a toroidal type magnetic core in here, and that produces a field structure, which, or rather an electron flow structure. And you get a suppressed one pole and a more intense beam of magnetic energy in another pole. So again, looking at the Bogdanovich work, they published in 2019 this work where they observed these toroidal plasmoids moving around on the surface of the metal that had been exposed to the plasma flow discharge. And this was 2 days after the experiment. So whatever is going on here is able to maintain its sort of coherence for at least 2 days. And having spoken to other people, they in the US military, they were saying they've observed these things running around for about 2 months in electron beam treatment of military landing gear. And so one can imagine that these things are somehow feeding themselves from the environment and maintaining this state of luminescence. The other thing is they observed what appears to be crystal-like structures of these other smaller toroidal structures, where they are rotating around their own axis and around the group axis. And I believe that this could account for some types of strange radiation track that have been observed. So that is the context there. However, prior to this 2019, we shared in 2018 on December the 4th, this observation in another HHO. So this is HHO and this is HHO. This is what we call like you have a microwave diode, and you have you have a capacitor, and you use create a very intense discharge for the collapse of a sort of a inductor coil from a car, and you create a spark, and water's placed in here. And in one of these sparks, between the sparks, there was dark, but the next spark seemed to energize a plasmoid here that were with probably some sort of evanescence or some sort of disruption field that's going through the environment here, and we get a very similar structure to observed by Bogdanovich et al. This actual video was produced in May, was published first on May the 2nd, 2016, but like I say, we observed this and thought it was interesting on December the 4th, 2018, and in May 2019, this was published by Bogdanovich. Ken Shoulders on EVOs, he's saying now electrical engineering does not let charge disappear, but it does in this multiple toroidal form. So he's claiming that the EVOs can contain hundreds and billions rather of electrons in some form of toroidal structure, and that it enshrouds stuff and that it can enshroud it to a point where it disappears, the material disappears, and it can walk right through things. He also argued that the charge is not conserved, the energy doesn't appear to be conserved, something goes, the charge is screened, and he can change the charge on it 1 billion to 1 very, very easily, so it can walk right through things. Okay, so I think Takaaki Matsumoto, Dr. Takaaki Matsumoto, he published this paper in 1997, and we are putting these documents out at the moment. But this was electronuclear collapse experiments, and you can see the experiments down here. They're very, very simple. And in the case of the S70 experiment and N71, there is no carbon involved. Now, he was using AC voltage at 120 volts, and because he's putting it in potassium hydroxide 1.5 molar in water, light water, he will be creating HHO, even if he really, really, really doesn't want to. He will be creating HHO. So this is effectively an HHO experiment. And he observed that with a 1 millimeter lead ball for a very short experiment using the potassium hydroxide solution, that he produced these spheres, and at one of the poles of the spheres there were these plumes, and this is lead. There's no carbon in this experiment. There is potassium hydroxide and there is water and there is a lead wire, and he gets these spheres, and out of the pole of the spheres he gets a plume of carbon. And this is a nice example of this. So here is the sphere of lead, and out of the pole there is this flower of carbon, and it's like blown out, and it has these little ripples on it, and we'll come back to this later when we look at the Омасы gas. Again, this is HHO, and he says eruption of carbon film from PB ball. Obviously you've got 204, 205, 204, 206, 7, 8 or whatever here nucleons, and here you've only got 12, 13, not 14, because it won't be creating radioactive carbon. So you can obviously get a lot of carbon out of lead if you work in this way. And here is another example of the hole typically, and the plume of carbon coming out. And he also observed a lot of carbon film. So the reason I'm talking about these is because this is taking a very heavy element and synthesizing carbon film from that heavy element or carbon. And many other authors, for instance, Leclerc observed a predominance of the production of diamond from whatever he was using. In that case, it was aluminium and light water. So carbon seems to be produced. And this is Takaaki Matsumoto in 2001, although he did say it in 1997. He said, very amazingly, it was also found later that ring products consisted of conventional elements, mainly carbon, not dependent on collapsed materials. So whatever you start with, you end up with carbon as a predominant output. And the experiment, he says that I have to apologize for an insufficient assignment made in Ref 5 that quad neutrons collapsed. It was made clear by later experiments that clusters that collapsed were atomic clusters that could have a diameter of hundreds of microns and involve much more nuclei. So he's saying that this is the process called nuclear regeneration. Okay, so with that in context, we're going to get to someone who probably was one of the most well-known inventors of HHO technology, and that is Yule Brown. And he published, or rather the Imagine magazine published in 1988 this statement, The most startling claim by the inventor in the press is that the gas produced in his process can reduce nuclear and toxic wastes to harmless carbon. Using a slice of radioactive americium, Brown melted it together on a brick with small chunks of steel and aluminium. Now, the aluminium, in my view, is obviously very highly conductive, but it also likes to grab oxygen. It likes to oxidize. And so I believe that it's grabbing a lot of oxygen, like the tungsten was doing in Langmuir's tungsten filament light bulb in 1909. And it's producing, therefore, a lot of atomic hydrogen. And if we are to believe Matsumoto, in this case, it would be going to produce the ionic clusters along with the cold neutrinos that would be synthesized in the energetic process. And so then the steel, in fact, it's iron. The iron provides a magnetic hook for the magnetic monopoles to cluster until they go past the Curie point of iron, in which they are all released at the same energy, allowing them to become a coherent macrocluster and capturing whatever it is that's the radioactive material and doing a self-compression collapse, leading to the production of harmless carbon. And this phenomenological concept of the process certainly would account for all of the observations where he saw a near instantaneous 99% reduction in americium with this flash that occurs. And I believe the flash occurs when the iron that has aggregated these monopole type structures and goes through the Curie point and releases the magnetic monopole type structures. Okay, so we're now on to Омасы gas, and I think we need to start with the Омасы vibrators, and these are vibrator plates which have steel predominantly, and in the gas producing device it's either oppositely charged plates, or the vibrator will pass its water through some electrolyzing plates. So that's the way the Омасы gas is made, and you can go and look at Dr. Royshin Omasa's patents for that. And here you can see when it plays that there is this is high speed photography, and I think this is slowed down 8 times. And when you look at this with a keen eye, you will see that things are produced, cavitation bubbles or structures are produced on the plates, and then they travel around in the water. And when we were looking at this, the actual vibration of the system is running at around the main frequency here is 166.24. So that is the main, the primary vibration frequency of the vibrator. But with this 384 kilohertz mic, which can resolve up to 196 kilohertz, you can see that there are high frequency components, albeit at a lower intensity, all the way up the spectrum. Obviously there's some large number of decibels below, so this is what -6 dB here, and this peak is in the kilohertz here, and this is in the 40 kilohertz or whatever, but this is -20, this is -23 dB below, so it's quite a lot less energy. However, if you're getting resonance in any of these frequencies, then obviously the resonance, if there's a high Q factor, will not be lost. And so I speculated that we would see cavitation, even though we're having this very low frequency here on the plates. And immediately, having taken a photo, I saw these spots, which largely appeared to be in pairs over the entire surface of this plate. And the interesting thing is it's incredibly fault tolerant, this system. You have resonant modes that go along the width, along the length, and along this is the width, the length, and the height of the plate. So you don't have to be precise with this system, because the resonant nodes will find wherever they need to be resonant. And so there we go. And what do you see if you look under a microscope at these structures? Well, you see these hydrodynamic pairs. Here's what I call a perfect one, a figure of 8. And you can see the intense influence at the center here. Okay, very, very, very intense at the center here, and you can see this sort of less marked area and then something going on the outside. And here's 2 other examples which are less perfect than this. And they seem to produce these things that fly out, and you can see it's like a toroidal structure, and it's got some sort of poloidal movement around it. And this one's sort of died on its side, and this one's impacted like in the center here and like kind of blown up. So that's the structure there. So I was interested to see if you could get some sort of strange radiation tracks coming out of these, because I needed to try and, I wondered how you could create such incredible gas just from vibration and electrolysis. And in preparation for this, I bought a polarizing filter and on a microscope. And you can see here on this slide, I have the Dynolight Edge 3 over here, and I'm adjusting the polarizer on the bottom. And here's one of the steel plates. And here you can see what you can see with no polarizing on. You basically can't see anything of any use. It's just a load of specular reflections. And when you turn the polarizing filter on, you see here's our cavitation spot. And from the cavitation spot, we see a strange radiation track coming out. And in fact, it's going over to what appears to be another strange radiation track. So you can go and click on this when you get the PDF of the presentation here. You can go and click on this and you can go and watch the video of me doing that live. And literally, this was the first night we were there, having taken this plane at home. I had the microscope with me in Japan, and there we go. We've got it straight there. And I believe that if we look at here, this is the spiral track coming out of the center of the cavitation spot. And I believe that this is cohering matter. And in fact, Leclerc said that his water crystals were the seed of brown gas. And I think probably what they are the frozen coherent matter, his water crystals. But I think the coherent matter that's synthesized in these intense vortex structures with the charge separation that's going on, with the plasma that will be produced, will be producing an intense magnetic structure, a sort of skyrmion, but in the hydrodynamic synthesis way. And this will lead to the production of coherent matter. Coherent matter will produce the necessary structures that are doing whatever they're doing in Омаса gas, which you will see as we go forward. So here are various things that we also witnessed on the Омаса gas, as the Омаса vibrator plates. So we see the ring impact structures extremely similar to those observed by Takaaki Matsumoto. And we also see this structure with another structure that was very clearly observed by Takaaki Matsumoto. And you can see this pentagonal structure in here. And he says that these are sort of frost of itonic frost of hydrogen. So that's what he is saying that those are. And here we see this again, using the polarizing filter, a very, very classic braided, almost like three interacting structures of a strange radiation track. Now, my view on this as we go forward is that the incredibly intense magnetic flux that goes through the coherent matter structures that are formed in both cavitation and plasma intense discharges and resonant structures that are formed in resonance systems, the intense magnetic flux does either one of two things. It changes it leaves behind some of its self-similar structure as it passes through the material, or the material is changed in its crystal structure as it passes through because of the intense magnetic field. If there is something left in there and there is this sort of a leave behind of some of these intense magnetic structures, the light that's coming in will be polarized by those structures. Or like in a sort of one of those magnetic viewers, as the light comes in, it's just because of crystal orientation that you are getting the polarization. And so this was my hunch that led me to think that I needed to take a polarizing filter to be able to observe these things. And I would encourage all of you to use polarization observation when you are looking at materials you suspect of having been influenced by strange radiation or coherent matter. So here on the left, you can see down the bottom, the 1993 Journal of Fusion Technology images published by Takaaki Matsumoto. And on the above this, on the vibrator plates, this is not a Омаса gas, this is the vibrator plates. We see similar scale structures with a similar field difference. And this is what Takaaki Matsumoto calls the itonic mesh. which encapsulates the matter, and we observe something similar, same order of structure here. And I'd have to thank Dr. Felix Scholkman for producing this particular image. On the right here, you can see the ultrasonic horn here that I have in, that I was looking at the sound in the water as well as out of the water. Now, he didn't only use straight steel plates, he also used palladium coated plates. So here we have some palladium coated plates, and this is quite nice because you can see that how really rather simple, I mean, it's not precise how these plates are produced. And as long as there is a bit exposed to the water, there will always be some resonant nodes. And it depends, you have an upside and a downside, and some of them will have different resonant nodes on the other side because there's influence between the opposing plates, which will change the resonant modes in the structure. But obviously some resonant modes are sort of like a harmonic, where you've got a high frequency here, and these are much lower frequency here. And this is similar to where you had other researchers using ultrasonics, like Tom Claytor and I forget his name just right now, but anyway, he originally used about sort of 42 kilohertz, but they went up to higher frequencies. Anyway, if it's resonant and there's no losses, eventually it will get to the point of doing something useful. And what are the sort of things that it can do? Well, on that particular plate that you've just seen, there was this figure of 8 structure here. And in fact, the figure of 8 structure becomes a kind of cardioid structure, a heart type structure. And they have center points here. And in the center points here, I observed by using the dialight's various lights that there was a clear crystal of something in the center points here. And when looking at this particular structure under a scanning electron microscope, I found that essentially it was a diamond. That was this clear structure that was made in the center. Here it is with just the electron image. And here is the overall structure that you're seeing here, this figure of 8. It's less resolved in SEM than it is in color photography, so color microscopy. So I would greatly encourage people to use various techniques to compare their samples between color microscopy, macro photography, and SEM images to understand what's going on. So this is this figure of 8 structure here. I call it a yin yang. And anyway, over on the right here, you see the element map, and we know that already that we have a diamond here in the center. Okay, so I guess that's this thing here, but anyway, or maybe here, you have these vortical structures going around, and these are magnesium, and in between the magnesium are chrome. Okay, and the interesting thing is that magnesium is double carbon and chrome is double magnesium. So it's almost like there is a pressure gradient. The more intense the pressure, bizarrely, the less alpha particles it has. So the diamond is obviously triple alpha, the magnesium is 6 alpha, and the chromium is 12 alpha. So there we go. So that is the structure that's coming around. So the actual vibrator plates themselves do cause fusion, and they also cause fission. I'm not going to go into the fission experiments that were done and the fluid analysis, because we want to get to the Омасы gas, but that did occur. And I spoke a bit about those in my ICCF 22 poster session. So you can go and look at that on the MFMP's website. Here, however, I decided to put some indium foil, because it was very, very soft, into the vibrator plate to see what would happen when you got one of these toroidal structures that's left of the vibrator plate and collides with it. Well, what do we get when we see that? We see in the center of the center, we see calcium synthesized. And on there's a kind of vortical structure with cesium. Cesium was in the mix, but it's being obviously captured by this structure as it traveled through the fluid. Silicon is this structure around the outside, again, sort of semi-vortical structure. So you've got calcium in the center, silicon here, and I think carbon is around this outside, and the crystals are just, yeah, like I say, they're the cesium. And then around the outside of the whole impact mark, you have indium. Now, this was only exposed for 10 minutes to the vibrator. And it went from being a very soft piece of metal to extremely hard, or quite hard, certainly a lot had changed with the sort of technical structure of the indium. Okay, so let's go to the experiment of Омаса gas. So the Омаса gas is produced in this vibration system and electrolysis system, and it's put in, and it's actually produced on the fly. And I proposed this experiment because in all of the experiments that I had observed in historical record, people had claimed that the Омаса gas was causing the tungsten to vaporize, i.e. it was melting. So there was all these side of claims about you're exceeding 3,600 degrees centigrade or something like that. When we put a bolometer on here, it wasn't really going over 1,000 degrees. And so that was interesting, but it certainly did fume. So I thought, well, you know, if I see some transmutation on this thorium-doped tungsten welding rod, no one's going to believe it isn't contamination because, you know, I could have contaminated it somehow. However, I thought, well, I asked Dr. George Eagley if he could use this vacuum cleaner. These were the things that we had available in the few hours we had to plan the experiment, and to use one of these face masks that we're all familiar with now, and to try and capture the fumes that were coming out to see if there was a consistency between any potential transmutation on the tungsten and any transmutation in the captured particles coming from the fumes that were coming off. So I'm going to show this video now, and you can see the entire length of the experiment here. So this is myself, this is Dr. George Eagley, this is Sho, thank you Sho for helping support this experiment series, and this is Dr. Roy Shinamaza, you can see over on the right here. So down here you can see the head of the vacuum with the filter on it, and this is Dr. George Eagley here. This is the tungsten welding rod. Now, as this is working, other researchers in HHO have found that the gas has different levels of hydrogen and OH radicals, depending on how close you are to the sample. So if you were to try and replicate this with some other HHO generation system, you would need to follow the kind of distances you are witnessing here. And I think this is a 3mm rod. So you can assess the distance here that was used during this experiment and know that you're getting a similar type of constituent gas. The flow rate is very high with the Омаса vibrator system. Okay, so that's it. That is the entire experiment. And so I asked, based on what you will see in a 10-yen coin, was the OH radical self-mazing? Because there is OH in there, but there's also water and H maze. But anyway, it contained 0.28% of atomic hydrogen. But like I say, if you're, for instance, exposing Омаса gas to titanium, for instance, or tungsten, or aluminium, I believe that the oxygen will preferentially oxidize those metals, and you will end up with a lot more atomic hydrogen produced on the fly, plus whatever is going on in the gas, which has these water cluster type structures, which I believe probably are held together by some sort of coherent matter in the form of some sort of monopoles bound to free oxygen in the water that's dissolved in the water. And one reason I believe Омаса gas is superior to normal HHO is that it's continually producing dissolved oxygen in the water, whereas other systems, because they don't have the vibration, they use up the oxygen first. And a lot of HHO researchers find that the first flush of gas is the really good stuff, and then after that it doesn't seem to do much. And so you need to be aware that you probably do need some form of vibration in your system to create the good gas. So anyway, the OH radical was subsequently sort of confirmed by Slobodan Stankovic in ICCF 22 when he observed an intense line for the OH radical. And those that know their cosmology will know that this self-mazes in the cosmos. And so he's talking about that here.
Analyzed with the low resolution optical spectrometer.
Anyway, so he talks about the OH there. This is looking at the tungsten welding rod times 100 under the SEM, and it's fairly smooth surface with some sort of annular rings on it. And zooming in to 1,000 times, I looked at the surface and a defect in the surface, and essentially you can see a little bit of a thorium creeping in, a low level of carbon, a little bit of oxygen, but predominantly it is by mass concentration a 80.22% by mass tungsten. So it's essentially tungsten. Now, what happened in the experiment that you just saw in terms of transmutation? Well, what happened is we see these plasmoid-like tracks running partially under the surface, and at the end of the track we have spheres of material. Okay, and if we analyze the spheres of material, which I've done here at the end of these tracks, every single one of them has calcium in, plus many of the other elements that are predicted easily by the Parkhomov reaction tables at nanosoft.co.nz. And if we look down the bottom here, obviously again, tungsten 180 is only 0.14% of tungsten. But if we look at 182 and 184, the next two most energetic reactions that can occur, they account for 57% of the tungsten, and they all fission to calcium. In this case, calcium 48 is preferred for the 184 and 182. So we might expect, if we could do some isotopic analysis, to see this calcium predominantly calcium 48. Now, what is actually happening when this is occurring is, I believe, that you'll get, like I say, there's tungsten oxide on the surface here, so you can see the oxygen here has gone up significantly. I believe a lot more atomic hydrogen is forming. You've got the clusters in the gas as well. They're forming plasmoids. They are forming exotic vacuum objects, which are partially burrowing into the surface and consuming the conductive metal. And they are synthesizing this range of elements. And because calcium is twice the atomic size of tungsten, this will blow the material apart. So it smashes it up and throws it up. So it's not so much becoming becoming a gas. What it's literally ripping the matter apart. And so I imagined seeing this, that we would see actual fragments of tungsten in the gas particles that are coming out. And the other thing is, we do see calcium in every single output, and as these are the most energetic products, this is not surprising. Nature wants to do the thing that fits it into a small box most. So calcium is actually, as I said, twice the atomic size of the tungsten nuclei, or so the atom is, and xenon is even bigger. So if we've got xenon being produced as well, the combination of these two produces an incredible intense pressures when the material comes back and gains their electrons back, and it just rips the matter apart. Here is another area we are looking at here. So I've done an area scan and so forth. But again, you can see in every single area, you see calcium, and then some of the other usual subjects that have been, products that have been observed by other authors. Now, I've talked about the plasmoid structures, the small ones here, but we observed potential influence of very, very large ones. So here, I believe we have two examples, a large one and a small one, which may be linked in some way, of plasmoids that are coming perpendicular to the surface, and they are, through probably some sort of dichotron instabilities or something, they are creating a hexagon shape here and a hexagon shape here. And so that is through the surface, and there's a little bit of sweeping the material around the edge. This, I believe, is one that is 50% into the surface, but parallel to the surface. So a lot of times when you see ball lightning, you see a hemisphere on the material. I will show you an example from our Vega experiments later on. And so you can see, again, there's a toroid above and a a circular structure here above and a circular structure here below. This is magnetohydrodynamic. This is a plasma structure, very similar, I believe, to the one that we observed in the hydrodynamic system in the actual vibrator plates themselves. And again, here's another look at some various materials. This is on the inside of that hexagon, on the outside of the hexagon, and you can go and look at this in more detail. But again, you've got the expected sort of transmutations going on there, and a lot more calcium here, as I had said earlier, and a lot more carbon than was observed in the original material. Okay. This is more of the same, so we will go on to looking at this structure. Now, the interesting thing about this structure is that, for instance, in this area here, we have, which is this, there's actually like a sphere that's at this point, and we see that this is 6.14% by atoms, iron, okay, iron, in this spherical structure that's embedded in the overall vortical structure here. When we look at this area above here, so there seems to be this vortex, and there seems to be this beam that comes down here, and it seems to be disrupting an area down here. And this is also a circular type structure, and it's split halfway between that, between the sort of almost the center of this, but not quite. And if we look at this film that's on here, we observe that this is 76.1%. Is it right? Where is it? 1168. 1168. Yeah, 76.1% of that film area here is carbon. And this is analogous, in my view, to the carbon film that is produced by Омасы in his observations. And we have seen this in many other systems. And again, you see all the other usual suspects that you see from fissioning of tungsten. Okay, so in the filters, we observed some chunks of much lower amounts of tungsten, but certainly every single sample we took, other than obviously the carbon, the actual this is the filament in the face mask, which is essentially 100% carbon and oxygen. This is just a polycarbonate or something. But anyway, looking at the other chunks around here, we see calcium largely in there, and there's a little bit of iron in some of them, and they seem to be fairly chunky. So this kind of goes along with my thinking that it is literally ripping the tungsten apart. So for me, the combination of the observations of material here, plasmoids eating the material slightly under the surface, the actual macroplasmoid structures here, and the transmutation all being in line with predicted transmutations, and the observation of tungsten and fission products of tungsten captured in the face mask filter. I believe that it's 100% doing exactly what was claimed by Yule Brown and by other authors. So we can see here the different elements, and you can look at this in your own time. So what do I believe is happening? I believe that these soliton structures, either half soliton or full soliton structures, are forming. I've shown you this image before, and they can produce a magnetic flux loop, and some material is destroyed by the yang, and it's carried over, and it's accumulated by the yin. And between the two, they can both destroy matter and rebirth matter, as it were. And here is just a 1950s image of this. There would be if I played it. So this is the hydrodynamic structure and the counter-rotating vortices that you see, and this was dusty water with an aerofoil to show the process here, which you're probably all familiar with. And these are some structures from other experiments. This is from the lion experiment, burrowing through the material, and this is on the outside of the lion. And the interesting thing about this is that the main big structure here is also made of smaller things that look similar to the big structure. It's self-similar. So it's like a cluster of clusters, and so you can see the overall structure there. So Now, this is what's happened in the last couple of weeks. Someone from the Sapphire Group sent me this soliton paper, which was published on the 21st of April 2021. And this is a collaboration between the US, UK, Czech, China, Japan, and Portugal. And it's funded by the US Department of Energy, the European Union, and China in many ways. And it's conducted at many Chinese universities and a major US lab. And what they're doing is they have a laser pulse production of solitons in plasma, and they want to combine a synthetic simulation of that to find out what's going on and compare that to the observed phenomena that they have seen. So let me just go back to that. And so the paper is Dynamics of Moving Electron Vortices and Magnetic Ring in Laser Plasma Interaction. They do one laser pulse, okay? And if we look at it here, it produces, this is on a plane. So they are looking at the north or the south, or the north and the south vortex. Let's say they're looking, let's call this the south. There are an inner current and this outer current and the capture current here. And they are saying that over this 2 micron distance in the head of the side of the soliton, there are, if I'm reading this right, and I can't even believe I'm reading it right, but in this particular case where you have a near 50 micron, it's 48 micron structure. The reason they can't make it smaller is because of the width of the laser pulse. So they know how wide their laser pulse is, so they're simulating something that is similar. They are claiming that they're getting 1.8 trillion volts per meter negative, and across the sort of double there, they're getting positive 1.8 trillion volts per meter. I can't quite believe that, but that is a lot of charge separation that could do a lot of ripping apart of matter. And as we know from Uritzke's presentation in 2018, if you take all the electrons off, for instance, thallium-205, it will immediately beat to decay to lead-205. And there's a number of elements that are known to do that. Maybe there are a lot more elements. And I believe that if you have unstable elements, you will probably have many, many elements that will just fall apart. And that's just on the removing all of their electrons basis. But you can see here at the head of the soliton here, they're seeing intense electron bunching. And as we know, when you have electron bunching, that forces coherence of the electrons. And so I believe that they will be producing coherent electron matter at this point, which is in line with the observations of Shoulders and other authors. So it's a magnetic dipole structure. The electron vortices have a center speed up to 0.23 of Tesla. 0.23 of the speed of light. The soliton core current is in excess of 1000 Tesla, and the field is astronomical. So intense electron bunching would lead to coherence, in my view. And this would, and I ask a question here, would the extreme velocities and magnetic pressure of dense matter not lead to cold neutrino, antineutrino production? And if that is the case, this intense velocities and magnetic pressure and the density of the electrons and the other matter that's swept up in here, I believe that that fulfills very much the requirements of Alexander Parkhomov. This will produce vast quantities of cold neutrinos and antineutrinos. This will lead to a soliton that contains neutrinos and antineutrinos, electrons and matter. This is the building blocks for making itonic clusters. It is the building blocks to explain the observations of Alexander Shishkin and the observations of Alexander Parkhomov. And if this interacts or clusters into either a larger soliton or a spherical encapsulating itonic cluster and then self-compresses, then I believe that this will lead to baryon decay. So the soliton paper then goes on to investigate what would happen with the laser pulse in a 3D volume. And they see the vortex moving at a velocity of greater than 0.1 of c. And this is interesting because Ken Shoulders said readily EVOs can be made to travel at 0.1 of c. In this case, the field strength was 1.3 times 10 to the 3 Tesla. And so if the soliton formed from a single pulse and expands, the field drops. So they're just doing one pulse. And then afterwards, the soliton diameter expands and the field drops. Now, given that this is, in this case, I think this is 20 micron soliton that they have here. So what you're seeing is in this one, which is 46 microns, they've got 1,000 Tesla. And this one is 20 microns, and they've got 1.3 thousand Tesla. And so this is telling you that the smaller the soliton, the more intense the magnetic field. And so you can imagine that 1 micron might have a very much higher intense magnetic field and so forth. So I'm saying this implies a tighter soliton, resonantly pumped, not with a single pulse, would produce far more intense fields. And I believe this is true for hydrodynamic systems where you have sound resonantly pumping at nodes on the vibrator plates, energy, which is intensely producing cavitation, which will produce a plasma, which will produce easy water. So you have charge separation. And this will spin in a vortex, and it's charge pumped and charge pumped and charge pumped until you force the production of coherent matter, and therefore you get your strange radiation tracks. Now, Lutz Jaitner at ICCF 22 calculated that for his condensed plasmoids using quantum mechanics, that the magnetic fields at 9.2 kiloamps were up to 50 million Teslas, and that this magnetic pressure in the condensed plasmoids was exceeding 2 × 10⁻21 pascals, which is 5 orders of magnitude higher than in the solar core. And this results in nuclear density in the range of pulsars, which is a form of neutron star. So due to the intrinsic current of condensed plasmas, they will exhibit pseudo ferromagnetic behavior even at high temperatures, and other authors have observed this. So how did I get to the point of thinking how these systems were working? Well, in 2017, I saw this video. In fact, I actually recorded this video in Suhas Ralkar's lab in India. And what you are looking at there is a steel ultrasonic horn, and it's in water. And the beauty of this, what you're seeing here, is that this has been running for a long time. It's producing nanobubbles, which adiabatically compress and become dissolved in the water. I'm just going to stop here. They become dissolved in the water. So this water is replete, absolutely replete with nanobubbles of whatever was produced here. And so what you see sometimes in here is large toroids being synthesized, but also this one is a torus here. So you've got a torus here, and what is happening, in my view, is that as this is spinning round and it's pulling material in, it's depressurizing the water in front and to the sides of the torus, this soliton that's moving through the water. And what this does is it causes the bubbles, the nanobubbles that are dissolved in the water, to re-expand. And so this white bloom that you see here is my torch reflecting off the bubbles that are reforming because of the depressurization in front of the soliton to the sides of the soliton, and interestingly, in a beam that goes down its azimuth. So if you can imagine there's a ring soliton in here, and it fires out this beam, and it's depressurizing the area of water in its azimuth behind it. And this also causes a production of the observation of the nanobubbles reforming in the water. This, for me, in 2017 was probably one of the most interesting things I'd seen. And here you can see a Lord Kelvin type smoke ring. And again, you see these, the particles coming through, and then they're going to the side and going to the side. And you can imagine if they're going to the side, they will be depressurizing the zone in front of the soliton. And hence it probably aids to the moving forward. And again, things are being sucked in from the back down the azimuth of the soliton. This is the depressurization here. This is the depressurization here. And this, again, this is from Alien Scientist channel. And you can see apparently a slightly different field, this dome above, where you have the soliton here. Okay, so essentially this is smoke and air, smoke and air. This is CO2 and air and condensed air forming the white ring here. This is hydrodynamic, and hydrodynamic producing this bubble mark. But for me, this is probably the most important observation I had in 2017. And why do I say that? Well, look at not that, but this. So here is my soliton structure with the depressurization zone here and the depressurization zone here. What we have here is again a depressurization zone over here, and if you trace the vortices that come down, that there is a coming together of those vortices at this point where this sphere is, and this carbon film is produced. And I believe that there is a disruption that comes down here, and because this is an electrodynamic structure and it has a magnetic field, I believe it is pulling relic neutrinos potentially, or some other influence through this azimuth, and it is literally destroying or disintegrating the matter at this point. And it's converting the tungsten at this point into basically alpha particles, which settle down as this carbon film here, because they're basically torn apart. It's literally tearing matter apart. Again, the vortex here. This is in the 10 yen coin we will look at here. And again, this is a magnetohydrodynamic structure in the plasma, I believe. And we will look at the side here where we will see microball lightning. This is, I found, in the 225-day reactor of Alexander Parkhomov. Again, you have the vortical structure here. And you have there's an iron sphere similar to we observed here in this on the reverse side. And in fact, I was able to roll this around in the electron microscope by firing the beam at it. It responded to, it jumped away from the electron beam. So it was a bit difficult to manipulate, but actually I got it to flip over. And so on one of the corners here, you see a similar sphere, which is rich in iron on this structure. And I shared this at ICCF 22. And this is from Ignition Secrets. And this is a HHO plasmoid being produced by an electric spark here. So I've aligned these up to be in a similar order. So this is a full soliton, depressurizing the environment around it and behind it, and producing the nanobubbles. This is in a hydrodynamic system. This is a magnetohydrodynamic, magnetohydrodynamic, and this is magnetohydrodynamic. This is with water, and this is with water gas. This is with water gas, and this is in Alexander Parkhomov's reactor. Okay, so if you can imagine this structure, we're now going to talk about the details of some experiments, but this is from our Boger experiment. And here is the half plasmoid that you typically see, which would be equivalent to this structure here on the surface of a metal. This is a full plasmoid because we actually have a metal foil around here on our anode. And if we energize this with sufficient current, then this will start on the coherent matter layer, the inside of the double layer. It will start consuming this material, and it actually doesn't matter what material, what element we put in here. We put tungsten, we put nickel, we put titanium. It just, when you get them formed in a sphere like this and you drive it to the point of sufficient intensity, it will start consuming the matter. And so it's very interesting to watch. This is actually done by an Indian using razor blades, a PET bottle, and some water and a 12-volt battery. And this is a hypodermic needle. And you have a capillary instability here, and as the material comes out, it produces a vortex, and you get the same sort of ball lightning type analog structure, but not at the intensity that it destroys matter, because this is in free air and this is in a low pressure environment. So one experiment we did was with pure titanium sheet and with a polymer of carbon and fluorine, commonly called polytetrafluoroethylene. We treated the material for a few seconds with a Marsa gas, and we pushed it down at 90 degrees to a piece of Teflon. This is the aftermath, but I'll show you the experiment first. That's the experiment. And in part of the experiment, we saw this zone of crystals. And when you look at it under the microscope, you see it's a very, very ordered dendritic structure with open voids. And it has these sort of polar structures. They are kind of like, they're self-organizing on this overall self-organized structure. And they have cones and rods, cones and rods. And if you examine the cones from the base upwards, you end up with, at the very base, you have nickel, then you have iron, and then you have chromium, then titanium, and then the rod is made of a carbon, is like a carbon nanotube. And so what it is the I believe that the plasmoid has each of the little exotic vacuum objects have grabbed some titanium atoms and they've grabbed some carbon, and they are dumping carbon. Where we got it here? They are dumping carbon plus titanium, then beryllium plus titanium, like 2 alpha particles, then alpha plus titanium, and then they've just got titanium, and then when it runs out of titanium, it just dumps a carbon nanotube. And so that's what you observe. And in fact, Solin saw these cone and rod type structures in his work for his 1992 patent. And he says superconducting nuclear condensate is magnetic liquid metal nuclear fuel that generates energy with generation of coherent radiation. It produces nuclear phase transformations, blah, blah, blah. In particular, carbon, nitrogen, oxygen, potassium, calcium, sodium, aluminium, magnesium, and silicon and iron. And he was using zirconium in his reactor. So based off the Solin patent, he's saying the physical process in this substance are similar to those that occur in superfluid, superconducting nuclear plasma neutron stars. Obeys the laws of Bose condensate and acts as a classical coherent wave. Therefore, it is detected spontaneously without chemical etching of the nuclear fusion product. Due to the implementation of coherent ultra-fast explosive crystallization, it consists of many fragments and dispersed areas in the form of ordered clusters of microcrystals, which are separated from each other by voids. In the background, you see what we created in that experiment. These are ordered crystals of microcrystals separated by voids, which he says is caused by the implementation of coherent ultrafast explosive crystallization. So what we are seeing here is titanium plus alpha conjugate nuclei, all the way from titanium through chromium to iron, with carbon as the source and titanium as the source. Now, if we look at the fluorine, there's this piece of fluorine, PTFE rather, that somehow ended up partially into the titanium, and it has a plasmoid that entered on the front leading edge halfway through this section. So I believe that there's some sort of field around this that almost teleported this whole chunk of material into the titanium. And you can see the plasmoid burrows in, and then it takes a change of direction, and then it comes to its demise here. And this is actually pointing in the direction of the material that you have just seen. And if we look at this material and compared to the material outside, you will see that essentially the material outside is much higher proportion of fluorine, and the material inside are alpha conjugate nuclei on fluorine. So fluorine to sodium to aluminium to phosphorus to chlorine and so on. So obviously you're going to get calcium with these things, and obviously you're going to see some titanium, and the iron is coming from the titanium. So here you are seeing alpha conjugate nuclei on fluorine. None of these elements we see from the same experiment on here when we are looking at the titanium. We see alpha conjugate nuclei of the titanium. So in both cases, we've taken a fermionic isotope and built alpha conjugate nuclei off it, and we've taken a bosonic isotope and built alpha conjugate nuclei off it. And so you can see a close-up look of where the plasmoid died, and if you look at different spots in here, we were even creating copper and stuff, and there's the nickel is appearing there again. So under the Parkhomov reaction tables, I do the single isotope and multiple isotope here to create the various elements that were observed. And in almost all cases, there's no need for neutrinos. It's just a combination of the nuclei from fluorine compounding with helium. So the next experiment we did with the Омасы gas was on a 10-yen coin. Thank you to my colleague for suggesting this. Dr. George Eagley, and you can see the experiment here. There we go, that's the experiment. And on the side of that, we have this structure which I showed you earlier, which is a magnetohydrodynamic structure in my view. And you can see some little microscope work here to give you a better idea of what we're looking at. I believe there's another one here that's nearly orthogonal to it. There's another impact strike here. So many of these sort of miniature ball lightning or miniature plasmoid structures were coming off the main plasmoid. And if you look here, this structure here is very similar to a synthetic monopole structure that was produced in a simulation and published in Nature at Aalto University. And so I believe we are seeing this beam that comes down here, and the monopole, whatever it is causing the disintegration of matter on the tungsten. Now, what I'm going to look at, so this would be the yang, this is the destroyer, and this is the yin, and so this is the builder. So I believe that the soliton in this instance is coming around this way in the magnetic flux loop. And if we look at this side of it, so bearing in mind that this is a smaller version of the overall side. So this is the coin which was exposed. So this is the yin, this is the, this is the yang, this is the yin. So the material was consumed from here and thrown down on here. Okay, and these are largely carbon and silicon kind of deposits and products thereof. On the perimeter of the overall large plasmoid here, you have this area here, which I've blown up here, and you can see the structure that we're referring to here, which is like a small version of this, but at 90 degrees or to the overall plasmoid surface. And in this side of this structure, we have this here. And when I observed this sometime afterwards, we observe these spheres moving around like snowballs, running down a mountain, like Tesla would say, and accreting material. And this is oxygen on, this is copper oxide on top of the copper. So this is predominantly copper, and these materials are moving around. And I think this is akin to Bogdanovich's long-lived plasmoids, and they were moving around and consuming the matter. And when you look at what they've done, they have converted oxygen into sulfur. So you can see down here, the oxygen here has become, it's produced sulfur in these spheres. So this is something that ball lightning is supposed to be able to do. And here we have what would appear to be not fusion with the copper. It seems to be just fusing the oxygen from the top of the copper. It's consuming it and moving it around. So this is what I would call a micro ball lightning. And it's inside one side of a mini ball lightning. And that is a structure that's on the side of a much bigger ball lightning, or rather magnetohydrodynamic structure. Okay, so that is on a copper predominantly with a little bit of zinc and some small 1 to 2% of tin, the 10 yen coin. We also applied it to some indium, and this was hair thickness. And as we know, indium normally melts at 156.6 degrees C. Well, it seemed to survive as good as the tungsten, and it glowed incandescently bright. And I believe that it was accumulating the charge clusters in there, the exotic vacuum objects. They were forming a mesh and even protecting the material, and they were emitting intense bright light. And it was so intense that you can see that you can't see hardly anything from the light in the room. You can see the fluorescent light on the roof here, but it changed the exposure because it was so intense, and it's still completely bloomed out. But here is a video of part of that, so you can see what happens. This is slowed down eight times, but it converted this hair thin piece of indium into something akin to a rubber sheet. This isn't melting. This is some other process going on. It's not real melting. But looking under the microscope, what do we see? Well, we see what look like volcanoes. And from the volcanoes, you have these plumes of material coming out. And so over here, what do we see on the plume of the material? 383, we see that is predominantly carbon. It's predominantly carbon. The indium's virtually gone, okay? And so this is almost exactly the same as Matsumoto observed in 1997. So we have indium here, not as heavy as lead, and it's spewing out this carbon structure. And in fact, the form of this structure is very similar to the structure that's coming out of Matsumoto's lead ball. And these are to the same scale. So they're certainly comparable in terms of the actual structure. So this one here at 40 microns across, this is 10 microns down there. So this is the same scale as this structure coming out here. Now, what I believe is happening is a coherent matter structure is going under the surface to a degree, and it becomes energized, and then it blows up. some sort of a coherent matter nuclear process going on, and it vaporizes some indium, and that comes into the air and oxidizes. And these crystals here are perfect octahedrons of indium oxide. And I think they come up and they rain down onto the indium, and then behind them, from the magma chamber, as you might call it, blooms the carbon, predominantly carbon, and sometimes with a little bit of silicon, depends on how intense it is, comes out of these chambers. Now, if you can imagine what this is, I actually think it's blowing a bubble, because I think what's in this hole here and what's in this hole here is actually this. It's a bubble of helium inside, and this is the one that didn't quite blow. It's like a dome that's come out. Here we've got one that's come out and blown and come to the side. And you can see that these are carbon here. This is carbon. And in this one here, this sphere that's in the center of this structure here, this has iron in it and silicon and aluminium, okay, in this particular bloom here. So all of the typical synthesized elements you see, sodium, aluminium, silicon, right in the center here. But this one is predominantly carbon here. Okay, and again, you see these carbon films. So here we've got these carbon films here that Matsumoto observed. We look at this, and this is 44% by 0.81 by atomic ratio here. So I've taken it off this sample here, and 402 here, sorry, 403 here, seeing again iron and silicon in some of the structures which are in the center of these locations. Now, from that same Yu et al. Paper on plasmoids, they have this other structure that they determined could be formed. And we see a very similar structure on the indium with material coming out of these arms in the same way that these are where the soliton intense vortices are. So they're coming out of the arms, not in the center, channels, not in the center, it's on the arms. So I believe that this structure may be something similar to that which was predicted in their supercomputer. Okay, so Омасы vibrator observations. We have production of intense resonantly driven hydrodynamic vortices. So here is the example. And we've replicated this in our ultra experiments. You can go and do that. It only costs $35, and you can transmute matter with it. And it takes about 20 minutes to learn and conduct the experiment. So here we go. We've got our intense resonantly driven hydrodynamic vortices. Like I say, all of this work was one laser pulse. It's not resonantly driven. This is resonantly driven. This is a resonant node. This is a sound node. And a node and antinode probably, and this is where the vortex are formed. The production of strange radiation, in my view, coherent matter tracks from the center of one of these structures to the center of another. So I think this is the flux tube joining together. This would be the same thing that produced the strange radiation tracks in Leclerc's work. Production of natto-like marks. The natto is the dough ball, the fermented ball of Takaaki Matsumoto, similar to those observed by Dr. Matsumoto. So this is again on the vibrator plate. So I believe that the coherent matter can cluster, and it can cluster and form something very special in the gas that aids it to do its work. And production of carbon conjugate nuclei. In this case, this is carbon conjugate nuclei, as I said, diamond in the center, magnesium on the vortical arms, and then around in between chromium. And it's dependent on some kind of pressure. Other transmutations not discussed were new elements, and they're synthesized in and basically this was in the liquid. So when the liquid was exposed to the vibrator plates, there were transmutations in there. And I discussed those at ICCF 22, and that would be a separate presentation. Now, on the Омасы gas observations themselves, we have production of microball lightning from a macro magnetohydrodynamic structure, and we see the aftermath of that with these plasmoids that have consumed oxygen from the surface of copper and synthesized sulfur. So that's that. We have production of intense magnetohydrodynamic vortex structures here, which are tearing apart the surface of the tungsten. This is, I believe, in parallel to the structure, these semi-sphere structures that you observe in plasmoids that you see in plasma chambers, and that it has an azimuthal a disruption channel, and I discussed how this is observed in a similar hydrodynamic model, where it's literally ripping the matter apart down this azimuth. And then the fission of tungsten and indium. So we got the fission of tungsten here and indium over here, which we talked about, and this is equivalent to the fissioning of fissioning of lead in Takaaki Matsumoto's very simple and easy to do experiments, and the production of alpha conjugate nuclei from titanium in this case and from fluorine in this case. So, conclusion. The Омасы vibrator plates appear to transmute both ions in solution and the metals it is made of by way of resonant coherence, potentially providing a much needed solution to radioactively contaminated areas in the world. Омасы gas applied to metals appears to act as instant LENR, causing large scale and immediate transmutation of elements. Since Омасы gas appears to fission heavy elements to safe elements, it should be suitable for treating dangerous products of the fission industry. This is expected, as it was claimed to have been shown by Yul Brown in the 1980s and 90s. So, thank you everyone for listening to me. I want to thank Alan Goldwater and Magic Sound Labs for the help with the analysis and the provision of the scanning electron microscope with EDX. To the crowd researchers that made this possible, and to the generous donors, in particular Charles and Show, thank you very much.
Bob, thank you very much for your very long but very interesting presentation. Questions, please. But before questions, я хотел бы сказать, вот тут были вопросы в чате, и, ну, Боб об этом говорил, но английский, и все это не так просто понять, поэтому вот одно из основных свойств Омаса газ — это то, что ведь вот оптическое измерение температуры вот струи, которая из горелки выходит, показывает, что там температура не очень высокая, порядка 600-700 градусов Цельсия, а она прожигает и расплавляет металлические стержни, температура плавления которых много выше, примерно в 2-3 раза выше. А вот наоборот Индий странным образом плавится, не плавится как бы, а горит, и возникают там вот эти странные взрывы на Индии. А Индия очень легкоплавкое вещество. Вот там кто-то задавал вопросы, я вот пояснил. Пожалуйста, вопросы, вот руки поднимайте, пожалуйста, руки, и я буду давать слово тем, кто задает вопросы. Но пока только вот Анатолий Климов поднял руку. Анатолий Иванович, пожалуйста, ваш вопрос. Кстати, можно, друзья, вот, может быть, Толь, подожди секундочку, вот, может быть, немножко боятся вопросы задавать, вот, но давайте мы тут, так сказать, вот пытаемся соединить англоязычную и русскоязычную аудитории, поэтому я знаю, что у Боба работает Google переводчик, онлайн Google переводчик, поэтому можно пытаться задавать вопросы по-русски, вот, и он там кое-что поймет, потому что это его тема, и он поймет, в чем смысл вопроса, несмотря на то, что Google переводчик, конечно, работает очень криво, поэтому не стесняйтесь, и по-русски можно задать вопрос. Итак, первый вопрос Анатолий Иванович Климов, пожалуйста.
Bob, thank you very much for your interesting presentation. Very large, many questions, but it's a very important part of your presentation concerning to the chemical composition of the target. And if I understand you correctly, in all your experiments, you observe the chemical elements from the carbon up to ferrum.
Yes.
And if I look the Mendeleev table, I see that there are no nitrogen, there are no fluorine, there are no phosphor,
Fluorine.
сера, как sulfur, chlorine. And what do you think? Why some of the elements change each other very close to each, but another element are absent in your row, in your experimental results? And why? And second question concerning another very difficult question: why the chemical elements higher the mass than the zincum, cuprum, zincum, are absent in your results? Only light elements, not heavy elements. What do you think about that?
So I think
one minute. Я вот для русских слушателей, значит, хочу задать Бобу вопрос, который меня очень удивил и который, ну, коррелирует с тем, что вот я вчера встречался с Русковым, значит, обсуждали как раз вот трансмутацию элементов. Значит, мы видим странную вещь. Значит, трансмутация легко идет до цинка. Дальше она почему-то застопоривается, не идет дальше. Почему нет тяжелых элементов? Первый вопрос. Второй вопрос. Ну, если вы посмотрите вот результат, который Боб приводит, ну, с углерода почти вот идут друг за дружком все элементы там, но некоторые отсутствуют. Допустим, значит, вот азота нету, значит, фтора нету, значит, хлора нету, значит, ну и так далее. Вот я спросил, значит, Боба, что он думает об этом, вот о таком расположении элементов в эксперименте.
Okay, so on the first question, we are testing with EDX. We don't have a gas analyzer at that time in Japan, and not at the time when I was doing this analysis in 2019. We do have a gas analyzer now, and we actually have a original Brown's gas BN 2000 generator in America, and we intended to analyze for gas production from the beginning of 2020, but we've not been able to travel for 2 years. So it would have been interesting to see what the gas products were. I believe that we will see gas products in there, and the most excited I am about is the sister product from the calcium, which would produce xenon, which obviously is a fission product that's heavier than iron, and it's the sister product that should come from an exchange reaction with, or the fission reaction of tungsten. So, and I would like to see helium and these things that we should be able to pick up with the mass analyzer, the gas analyzer. So what we want to do is, like I was capturing the dust with the vacuum tube, I would have a filter capturing the dust, and then we would have the sample tube going into the gas analyzer, because it's a process gas analyzer, and we would observe the gases. So I believe that the gases are present, but they are lost to the environment. I think probably if the other thing that I wanted to do was to use a spectrum analyzer to observe if there was spectra from gases. And in fact, that's one reason why we bought a spectrum analyzer, and another person in readiness in 2020 bought several and developed specific spectrum analyzers to look for the gases we expected. Obviously, if xenon's produced, that's many, many different lines, but other reactions produce other noble gases and so forth. So we would expect to see these lines there, but we just simply have not been able to go to Japan or America to do the obvious testing to establish whether there was gas produced. Okay, so that's one thing. On the other case about iron, I think generally there does appear to be some strontium, but I think that's just a band overlap on the EDX. I don't think that's genuinely produced. And I think in liquids, you do see some heavier elements produced. And I think that's because the environment is slightly different. I think if you're in an air environment, I don't think you generally see anything more than iron. And in fact, we see in many different systems the production of iron oxide, iron and oxygen rich crenellated magnetic spheres produced typically in almost every type of system, from the ultrasonic in water systems with an aluminium foil all the way through to the plasma systems. And in these systems, you see this production of iron. And it seems to be those elements which are most of what life needs is what is produced by this system. I call it like it is the flower of life. It's blooming, and what it seems to synthesize are all the elements you need to make life, rather than the heavy metals and so forth. I'm not saying it can't produce heavy metals, because if you the thing about this is subtle cavitation. His vibration plates are only moving, as I showed you on one of the early slides. They're moving with a main frequency of 166.24 hertz. And this is not so intense energy. If you look at what was done by Leclerc, he actually had in fixed position aluminium, and the water was cavitating through holes. And so any cavitation point would be driven and driven and driven and driven and driven. And so it doesn't get a chance to settle. It's overdriven, and he produced every element in the periodic table and transuranics and so forth. I'm not interested in trying to kill myself, and so I'm not trying to develop systems or look at systems that are producing more radioactive waste. I'm looking at things that work and work down the table. So I think if you did a Leclerc system, which is relatively simple and it's well described, the stuff that he did and work with the US Naval Labs, it's a perforated aluminium sheet which is rolled up into like a carpet roll, and then he puts a high pressure pump with a pressure drop in. It produces cavitation, and on the edges of those perforations he sees production of diamond principally, which is carbon, but also all the elements in the periodic table. So I expect if we drove the system too hard, we would see it, but I don't think we do, because we're not doing that.
Боб, one moment. Значит, ну, он как рассказывал, так и отвечает. На самом деле, значит, очень трудно понять, потому что мешанина полная. Значит, вот он говорит, что ксенон действительно было трудно там, значит, регистрировать, потому что это газ, и потому что, так сказать, но он уверен, что ксенон всегда уверенно будет регистрироваться в экспериментах, вот где он использовал вольфрам и ну, тангстен, вольфрам. Вот. Все остальное, ну, это вот намешано, так сказать, и даже я плохо понял, значит, что он отвечал. Вопрос был простой, Боб. Значит, вот если взять Омаса gas, if you have Омаса gas experiment, you have chemical composition in your slides.
Yes.
And I see carbon, then oxygen, then another elements like potassium, magnesium, aluminium, and so on. But very in the Mendeleev table, these elements are located very close to each other, but some of the elements from this table are absent. My question, why? Nitrogen is absent, phosphor is absent, sulfur is absent. What do you think about this?
Well, we observed nitrogen in the vibrator plate deposition, but yeah, there's no
Омаса gas experiment, only Омаса
okay,
gas,
so
not vibrators. It's very huge number of the experiments in your presentation.
Yeah, so Омаса gas has CO2, the concentration of 0.12%. So the amount of carbon in there is extremely small. So I don't really believe that these large films that are organized in the material are from carbon. There is nitrogen in there, yes, and we're not seeing nitrogen in the analysis. That's true. And maybe for whatever reason that the nitrogen isn't playing a role or forming nitrides. Hold on, I just need to check the Омаса gas on indium, because there might be a nitride in the indium. Let me just have a look at that. Yeah, so if I haven't got the slide to show you, but in the atomic concentration on the surface of the indium. Let me share this slide here.
Okay,
I'll share it here.
Okay.
Because nitrogen is the biggest gas that's in Омаса gas, or rather it's in the air, definitely. Let me just
show us.
I'm sharing it. I'm sharing it.
Он не понимает твой вопрос. Он твой вопрос не понимает, к сожалению. Bob,
okay,
Bob,
so
Bob, you don't understand the question.
Maybe I don't.
The question of Anatoly. The question is why light elements exist in your experiment, but heavier experiment doesn't exist. And second question, why line in comparison of table of elements, some light elements exist, but there are void area between elements isn't filled with the generating elements. Two questions.
Well, for instance, I'm saying
why no heavy and why there are void areas of elements.
I don't believe in our
short
system.
Question and short answer.
No
time.
Bob, show us one of the slide with the Омаса experiment. Is not good because of this ion isotope. But another slide, please. You have composition.
Okay, so
another slide, please.
Омаса versus tungsten. Show, please.
Okay, yeah. I don't think you're seeing nitrogen because it's not an alpha conjugate nuclei.
That's good. That's good. I see. Carbon, nitrogen, oxygen, fluorine, and so on. But the number of elements are absent in your slide. For example, vanadium. For example, magnesium. And what do you think? Why these elements are absent in your table?
Well, I would probably say that vanadium is not there because it's not an alpha conjugate of titanium. So if you look at the top two that I'm circling here,
I see titanium.
Yes, titanium plus alpha goes to chromium, goes to iron, goes to nickel.
Just a moment, Толя. Он сказал, что по его мнению, вот одна из версий, по его мнению, показаны элементы, которые из альфа-частиц можно построить. Вот его идея.
Нет, это результат. Это результаты измерений. Ты посмотри.
Ну да,
результаты измерений. Поэтому
лучше не получится ответ.
Вопрос простой.
У тебя есть еще вопрос?
Вопрос простой. Почти вся таблица Менделеева, почти каждая клеточка, но ряд элементов выпадает.
Но он не ответит на этот вопрос. Isn't answer on this question. Толь, еще, наверное, может быть, у тебя есть, а если нет, то вот еще есть люди, которые хотят спросить.
Все, thank you.
I mean, very simply, I don't believe there's any vanadium there because you're starting with titanium and you're putting alpha conjugate nuclei there. So you don't see vanadium because it's not an alpha conjugate of titanium. Alpha onto titanium makes chromium, alpha onto chromium makes iron, and alpha onto iron makes nickel.
Ну, это нечто типа квантования по альфа-частице. Окей, Боб, thank you very much. Next question. Следующий вопрос. Bob, my question is it good if our participants will put your questions on Russian? Could you understand this?
I could try. Let me have my translator up. I will
if
try.
you can't to understand, we will try to
translate. Let me try.
But now give us possibility to put your question in Russian for better understanding.
Let me try.
Okay. Евгений, пожалуйста, вопрос, и можешь задавать его на русском, но, пожалуйста, без путаницы. Евгений, секундочку. Без путаницы, четко, коротко, потому что Боб будет понимать твой вопрос через переводчика. Пожалуйста.
Вот я и хотел сделать это предложение, что если Боб так
без ля-ля, давай вопрос. Так?
Да я хотел бы ответ дать вот Анатолию Климову.
Ответы потом. Есть
что вопросы? Все понятно. Если бы Климову такое оборудование, так можно
понятно.
было бы еще и не то получить.
Без комментариев. Но, Боб, no questions. Евгений Егоров, no questions, only comments, maybe later. Спасибо Евгению. Извиняюсь, что я вынужден прерывать, потому что, ну, вот у нас тут некая сдвижка по времени произошла. Я вижу, что вопросов больше нет, поэтому я хочу, Боб, let me put your questions. I have several questions, but okay. I'll try to put questions on Russian. If you don't understand, if you will not understand me, I'll interpret it. We'll try in English. Я поставлю вопрос по-русски, и Боб попробует меня понять. В одном из слайдов, Боб, вы говорите о парамагнетизме кислорода и его влиянии на результаты эксперимента. Когда возникла идея о влиянии, когда время, год, когда возникла идея о влиянии парамагнетизма кислорода на результаты эксперимента?
So, as I understand it, you're asking what the nature of paramagnetism is in relation
not
to
the nature, not the nature. I know the nature of paramagnetism of oxygen, but yeah. I asked you about when, year, when, time, year, when the idea of important of oxygen paramagnetism is important for the process you are studying now.
Oh, it can't be before 2000.
Which year?
It can't be before 2017, I don't think.
2000, once again, 2000?
2017.
2017. Okay. In Russian, I comment immediately. Мы с Барановым эту же идею выдвинули, когда возникла идея о темном водороде. И это было примерно в то же время. Очень интересно, что это практически в одно и то же время эта идея возникла. Следующий вопрос. Следующий вопрос. Сколько времени проходит от проведения эксперимента с омаза-газом до начала масс-спектрометрических или там других вот, по измерению элементного состава экспериментов? What time is between experiment and measuring of element consisting of the results of this experiment? Time, distance of time.
Yes. So the experiments were conducted in, I think, May or June or whatever of 2019, and the analysis was done in August.
Approximately
May,
June,
July,
August.
3 or 4 months.
Well,
3 or 4 months.
3 or 4 months. Okay.
They were sealed.
У меня еще есть вопросы, но тут возникла, значит, вот Сергей Жданов из Перми хочет задать вопрос. Сергей, коротко и четко, без уклонений, задайте вопрос на русском, если не получится, чтобы аудитория понимала. Пожалуйста, ваш вопрос.
Хорошо, спасибо. У меня вопрос простой. Меня хорошо слышно, да?
Сергей, не торопясь, он переводчиком.
Нет, я
не надо
проблем совершенно.
Медленно.
У меня английский хороший, проблем нет. Я просто говорю, меня хорошо слышно, да?
Хорошо слышно, да.
Ага. У меня вопрос к нему будет такой. Есть ли какая-то структура, да, то есть увеличение атомного атомной массы, да? Ну, то есть вот у нас элементы идут...
Сергей,
допустим,
Сергей, коротко и четко вопрос, без уклонений, пожалуйста. Или по-английски тогда пробуйте. Ему сложно с переводчиком.
Bob, is there any pattern between different atomic masses and like do they follow the pattern? Like for example, like there is a 10% of calcium, then it transforms into like 5% of some other stuff, other material. Is there any pattern like this?
I kind of looked at that. It's like it depletes the heavy atom to a much lighter atom, and then it builds from that point onwards. When you're starting with a heavy atom, when you're starting with a light atom, it's a progression. The more you push it, the more you get heavier atoms. And I think if you go back to Leclerc's work, which is a cavity system, I know, but it is the origin of this. He says that you had to exceed or go below 55% of carbon before you produce iron and other elements. And so if you look at my observations, you see typically here, this is carbon is 55, and there are some heavier elements being made here, but these are below this, and so there's a lower ratio here. So I do believe that Leclerc was quite close, but of course he's talking about a cavitation system, and we are talking about the exposure of the gas to a heavy element. So, but I do believe it's the same thing, and I think if you were able to stably impinge the gas for a long period of time, you may get some heavier elements. But I think because it's so dynamic, it just makes light elements, and you rarely get to see anything above iron, because the actual structures are magnetic.
Yes, but does it mean that, for example, like you've got an element like calcium or some or titanium, and then if it transforms into another element, so there should be a pattern following?
Well,
like
I mean, for instance, here, if you see sample 2, we've got a lot of calcium here, and the iron is the highest concentration when the calcium is the highest concentration. So whatever happened at spot 2, and it's over here, it's one of these sphere structures at the end of a channel. I think this one here, there's a sphere in here. This is one of the center, in my view, of the itonic cluster, the coherent matter structure, the ball lightning. And you tend to see production ultimately of a lot of iron and oxygen. It ends up mostly as iron and oxygen in these systems. Because there's so many light elements available to it, it doesn't want to push beyond there. It just consumes more light elements and moves them towards iron and oxygen.
And probably like a mass or area scan would be better in this respect, yes, rather than like
we need to do mass spectrometry, yes. So we
not mass spectrometry, but area scan. Rather than
so we've done area scans. So if you go to here, this is an area scan 1154, 1154 here, and you can see that there's in this whole area there's 0.86 of iron, 1.32 of calcium, silicon 2.3. This is atomic concentration, 1.67 of aluminium, but it's still 50%. So as Leclerc seemed to establish, you need to go below 55% to start synthesizing iron, and this is at 50.1%, and we're starting to see the synthesis of iron. So I think what's happening is, firstly, it needs to deconstruct the matter all the way down to carbon, and then it kind of builds up from carbon or alpha conjugates from there.
Okay, Сергей, еще есть вопросы или, может быть, мы...
Да нет, спасибо.
Спасибо, thank you. Толь, ты хочешь выступить или вопрос задать?
Нет, я хочу выступить потом в конце.
Тогда мы заканчиваем вопросы и начинаем выступление. Вот первый поднял руку Анатолий Иванович Климов. Пожалуйста. Но можно по-русски, потому что в первую очередь это нам интересна твоя точка зрения. Но, пожалуйста, говорите четко и не быстро, и он тоже поймет.
Уважаемые коллеги, я хотел обратить ваше внимание прежде всего на вот этот резак, который использует Омаса ГЭС. Значит, ну, что такое Омаза ГЭС, вы, наверное, поняли. Это, так сказать, в этом резаке присутствует, нарабатывается в том числе и атомарный водород. Значит, не просто водород и гремучий газ, а атомарный водород. Поэтому этот резак, он будет резать все, что угодно. Это атомарная сварка, так сказать, водородная. Значит, ну вот здесь он показывает, да, значит, сколько нарабатывается, вот, допустим, 0,23% там у него, значит, атомарный водород. Вот. В этом плане, значит, ну, я напомню, что вот эти атомарные резаки еще использовались американцами в ВМФ, значит, в Великую Отечественную войну они сваривали швы там, вот, когда корабли, значит, и уже в то время строили корабли, вот, сваривали корпуса кораблей. И уже в то время было обнаружено явление вот, ну, некой радиации, так сказать, многие сварщики страдали от облучения. Ну, это вот нам, эти данные нам Сверчков, значит, Андрей рассказывал. Вот, наверное, можно будет, так сказать, он их скоро и издаст, вы можете познакомиться подробно на эту тему. Так вот, обратите ваше внимание, что трансмутация элементов, которая получается, с чего бы он там ни брал, какие-то там монеты, какие-то там Индии, все равно, что он брал, у него начинается с того, что нарабатывается огромное количество углерода. Ну, в общем, факт не новый. Мы с Бараном и с вот, Валерием Николаевичем, значит, часто обращали на это внимание, что чаще всего при трансмутации образуется очень много углерода. Но дальше вы обратите внимание, за углеродом идут порядки последовательности, практически все элементы таблицы Менделеева. Значит, вот там и кислород, и там, значит, натрий, и магний, и алюминий. То есть алюминий нарабатывается на самом деле, значит, довольно много. То есть это как бы точка остановки. То есть как будто колесико вот трансмутации бежит, добегает до железа. Железа у него тоже много нарабатывается в его образцах. И, значит, и все. И дальше не бежит. Так вот, значит, я хотел бы обратить ваше внимание, что вот такие результаты, они получаются у многих исследователей. Ну, вот вчера я только встречался с известным вам Уруцкоевым Леонидом, который вот сейчас здесь Боб на него ссылался. Вот. И Уруцкоев тоже отметил, что вплоть до цинка они получали там при взрыве этих вот, титановых фольг практически все, ну, много элементов таблицы Менделеева, много. Но после цинка, как правило, вот эти трансмутации прекращаются. Почему? Значит, вот вопрос остается, значит, не очень понятный и остается без ответа. И более того, такое впечатление создается, что ну, добавляй один протон, и ты будешь катиться. Углерод добавил, так сказать, один, азот, кислород, и пошел. То есть, но коль скоро у них там это все быстро, вы видите, прожигается там буквально за 30 секунд. Но это какая же скорость этой вот реакции трансмутации, которая происходит за 30 секунд? Там, меньше минуты. То есть, ну, уму непостижимо, то есть похоже на то, что все это происходит как-то параллельно, все эти реакции запараллелены, значит, и вот есть выделенные места остановки, но если хотите, это, так сказать, солнечный цикл, который так на звездах творится, так сказать, там есть точки остановки, но они идут миллионы лет. А здесь-то происходит, как вы видите, буквально за секунды, десятки секунд. Там, значит, вот он ссылается опять на наших соотечественников, вот, Солина. Ну, все эти эксперименты действительно известны. Протон-21, все это известно. Я единственное, что хочу, вот все-таки резюме моего доклада, или вот замечания, или там подведение итогов, в том, что вот все-таки вот эти вот сразу одновременно все элементы появляются вот в результатах эксперимента, ну, в том числе, получается, теперь и Боба Гринье. Значит, он подтвердил, что трансмутация элементов – это подсказка, хорошая подсказка для нас, идет параллельно, то есть идет появление всех элементов сразу в таблице Менделеева, а не так, что вот какие-то выделенные есть там цепочки, о которых пропагандирует вот там сам Боб Гринье, что альфа-частицы – это вот исходный кирпичик. Нет, не исходный кирпичик, атомарный водород исходный кирпичик. Ну вот это вот мое замечание, то, что я думаю вот по этому поводу. Значит, а вот что за этим стоит, каков механизм, так сказать, этих реакций, ну это вот надо думать всем вместе.
Спасибо, Анатолий Иванович. Следующий Евгений Егоров, Владивосток. Прошу говорить медленно и четко по-русски, для того, чтобы аудитория поняла и Боб Гринье понял через переводчик.
Спасибо большое. Меня слышно? Все нормально?
Слышно.
Ну, что сказать. Вот, на мой взгляд, самым ценным вот в докладе является то, что уделено большое внимание тарообразным структурам, которые формируются в процессе обдува вот расплавляемого материала. И эти тарообразные структуры, вот, по представлениям, связанным с векторным потенциалом магнитного и электрического полей, они могут замыкаться на себя, и внутри них циркулирует магнитное поле, которое может достигать, ну, циклопических размеров. И вот в этом, на мой взгляд, и состоит суть того, что идут вот эти реакции трансмутаций. То есть в основе всего лежит энергия магнитного поля, которая, опять-таки, повторю, замкнута на себя и несет колоссальные энергии. Далее. Важно то, что здесь мы имеем квазидинамический процесс, когда струя, понятно, что сверхзвуковая, в которой нарабатывается и присутствует водород, и не просто водород, а молекулярный водород. А это значит, там присутствуют протоны, которые первично образуются. Ну а дальше уже все накручивается. И связано это с тем, что дебройлевские волны, которые, по сути дела, электромагнитные, обязаны иметь, просто в силу энергетики, вот в моей монографии это показано, составляющую торообразную, которая формируется, опять-таки, этот тор формируется не электронами, как Черепанов пытается объяснить, а эта торообразная компонента формируется векторным потенциалом магнитного и электрического полей, то есть сущностью, вариации которого по пространству дают магнитное поле, а по времени электрическое. И поэтому туда очень хорошо ложится максвелловская, так сказать, электродинамика. И представления, которые в конце концов, к которым, вернее, пришел Луи де Бройль. То есть вот волна пилот, в его понимании, это в основном тарообразная компонента. Ну вот, а в общем-то, конечно же, так сказать, эксперименты Анатолия Климова, они существенно богаче и по физической сущности, по постановке, но аналитическое оборудование, которым располагает докладчик, и которым располагают японцы, но это предмет зависти и такого тайного внутреннего желания. Спасибо.
Спасибо, Евгений, за комментарий. Черепанову слово. Пожалуйста, еще раз. Вот не понимают люди, переводчик, вот ваши отвлечения и междометия переводчик перевести не может, они запутывают. Пожалуйста, без междометий, четко и коротко. Черепанов, комментарий.
Я могу подключить демонстрацию экрана?
Нет, демонстрации не нужно. Мы говорим сейчас о докладе Боба Гринье, а не о ваших результатах.
Так нет, я хотел прокомментировать, собственно.
Нет, попробуйте словами.
Ну хорошо, давайте словами. Значит, то, что представил Боб Гринье, вот эта модель, когда квантами альфа-частиц набираются новые химические элементы, этот как бы механизм я предложил еще в 2016 году в переписке с академиком РАН Николаем Александром Всеволодовичем. Я написал статью о геологии и не только. И там представил все вот эти вот каналы, когда нечетные химические элементы через альфа-частицы синтезируют по цепочке нечетные, а четные химические элементы, ну, имеется в виду четные по протонам, они синтезируются, опять же, альфа-частицами и гелием-6. Поэтому здесь я как бы согласен вот с этой, ну, с этим предположением, будем так говорить, Боба Гринье. Теперь, что касается, почему, скажем, в каких-то экспериментах доходим до феррума, в других доходим до цинка. Ну, и я хотел показать слайд, в котором, скажем, в электролитической ячейке у Конарева он дошел даже до свинца. А вот здесь, мое мнение, оно состоит в том, что каждый эксперимент работает в своей магнитной структуре. То есть то, что вы используете в каждом эксперименте, оно различно. Но в каких-то моментах оно согласуется, и вы получаете, скажем, тот же феррум, да, в одних и тех же экспериментах, только потому, что это с точки зрения магнитной системы самое простое. Более сложное получить уже индий, там, например, там, или тот же вольфрам. Еще более сложная система магнитная должна быть, и магнитное поле должно быть создано для того, чтобы получить свинец. Ну, вот все, что я сейчас сказал, я хочу изложить в своем ролике. Я его уже презентовал. 4-я часть этого разбора.
Алексей,
она
давайте
будет
без реклам, мы сегодня говорим о Бобе Гринье.
Ну вот все.
Спасибо за комментарий. Тут вот, кстати, я забыл сказать, у нас тут вот выступал Егоров, и он сказал, сверхзвуковая струя, он сильно ошибся, струя дозвуковая, безусловно, струя Омаса ГЭС. Просто у нас тут разные посторонние люди, не посторонние, а новые, или, скажем, редко присутствующие участники есть, которых я знаю, которые хорошо знают, что такое сверхзвуковая струя, что такое дозвуковая. Поэтому...
Она снаружи
Нет,
но внутри соплавали, там сверхзвуковые скорости гарантированы.
Евгений, она везде дозвуковая. Все, спасибо. От вас не нужно комментарий. Спасибо. Она везде дозвуковая. Пархомов, пожалуйста, можно по-русски. Но я знаю, что Саша, Александр Георгиевич Пархомов всегда четко очень говорит. Саша, пожалуйста.
Ну, прежде всего, я хочу сказать большое спасибо Бобу Гринье. Прекрасный доклад, я слушал с большим удовольствием, прекрасные иллюстрации. Вот. Но это, так сказать, что касается Боба. Но я хочу дополнить то, что сказал Анатолий Климов. Действительно, образуются какие-то элементы, образуются так преимущественно, какие-то элементы образуются так, вот мы их почти не видим. Ну, с чем это связано? Ну, во-первых, конечно, образуются, я думаю, элементы те, у которых максимальная энергия связи. Ну, это, как известно, четно-четные ядра, и особенно, значит, устойчивые ядра – это те, которые состоят как бы из альфа-частиц. Но это углерод-12, это 3 альфа-частицы, кислород-16, это 4 альфа-частицы. Еще много образуется всегда кальция, а кальций – это 10 альфа-частиц. Вот. А что касается пробелов, ну, во-первых, те ядра, которые менее устойчивые, они менее вероятно образуются. Вот. И еще надо сказать, что есть же вещества, которые очень летучие, ну, например, азот. Почему его мы не видим? Ну, он просто улетучивается в процессе эксперимента. Ну и другие вещества, даже, может быть, они твердые, но они, так сказать, быстро возгоняются и уходят из зоны реакции, и мы их потом не видим. Ну, еще что? Значит, вот то, что образуются преимущественно элементы до железа и никеля, а дальше уже трудно. Ну, это относится только, когда обрабатываются, вот, подвергаются обработке элементы легкие, ну, такие, как, допустим, титан, опять же, и вот когда или тот же, так сказать, вот, ну, другие легкие элементы. Ну, почему? Потому что вот трудно перескочить вот этот вот максимум по энергии связи, который приходится на железо и никель. Поэтому идет реакция синтеза, идет вот до этих масс. Если мы используем легкие элементы, то там идет реакция синтеза, и они не могут перескочить этот предел. А если мы работаем с тяжелыми элементами, там уже образуются тяжелые элементы, и легкие там образуются. Когда там идет процесс типа деления, образуются более легкие элементы и совсем легкие элементы. Очень часто образуется гелий, конечно, в этих реакциях. Вот. Но мы его не видим, потому что его и анализировать трудно, и он улетучивается сразу. Вот. Вот из опыта наших экспериментов, когда мы работаем с тяжелыми элементами, действительно образуются тяжелые элементы. Например, вот когда мы обрабатывали сплав свинца и олова, то получалось серебро, и даже вольфрам получался в этом сплаве. Вот. А когда мы работали с вольфрамом, мы видели и гафний, и много ртути, кстати, образуется. Вот. А вот еще вот здесь вот Ирина Борисовна, значит, Саватимова, в ее экспериментах она работала с палладием, у нее тоже очень много тяжелых элементов возникало. Так что вот это вот представление о том, что нет элементов не образуются элементы за железом, это вот, так сказать, нет, это не так, они образуются все-таки. Спасибо.
Спасибо Александру Георгиевичу. Саш, ну я все-таки, да, молодец, что ты имеешь соответствующее образование, и поэтому ты вспомнил кривую зависимости энергии связи. Ну, ты ее назвал энергия связи, она еще называется энергия дефекта массы, вот, в зависимости на один нуклон в ядрах. Так вот, они же с индием работают, и с вольфрамом, сама за газом. Вот сейчас он показывает индий. Вот. Но вещества-то легкие, а индий-то тяжелый. Поэтому тут какая-то действительно Климов в чем-то прав. Значит, Вадим Гончар задает вопрос, почему-то у него нет видео, но, Вадим, можно по-русски, но очень четко. Пожалуйста.
Добрый вечер.
Чуть громче, Вадим, чуть громче.
Слышно меня?
Плохо слышно, чуть громче.
А сейчас лучше слышно?
Сейчас лучше, да.
Тогда еще раз добрый вечер, рад всех приветствовать. И большое спасибо Бобу за доклад. И я бы хотел прокомментировать, возможно, это будет банальщиной, но я хочу призвать нас всех не обманывать себя. Всем хочется получить, да, как можно больше результат, но большую часть того, что демонстрируют эти эксперименты, можно объяснить обычными вещами. В частности, когда в экспериментах, продемонстрированных Бобом, использовался технический вольфрам, вполне возможно, что эти примеси были в нем просто при нагреве, произошла передислокация, они собрались на межкристаллитных промежутках, сконцентрировались, и мы их потом увидели. Когда получают вольфрамовый сварочный электрод, не ставят задачу использовать максимально чистый вольфрам. Используется 96-98% чистота, плюс он прессуется из порошка. Соответственно, это не монолит, это прессовка, куда могут попасть и частицы пресс-формы, и смазочные материалы. То же самое касается монеты. В монете вообще используются металлы, возможно, там были и сульфиды, соответственно, сера могла поступить оттуда. Я не утверждаю, что это так, просто хотелось бы по максимуму исключить источники поступления загрязнений и сконцентрировать все внимание только на абсолютно, безусловно, синтетических элементах, которым нельзя найти источник поступления. Это как химики, о наболевшем. Потому как у меня в своих моих экспериментах четко работает правило, чем тщательнее поставлен эксперимент, тем хуже происходит трансмутация.
Спасибо Вадиму Гончару за комментарий. Он эту мысль, очень важную мысль, высказывает уже второй раз. И это лично я благодарен ему, потому что он еще и еще раз призывает
Could I
нас...
respond to that?
Sorry?
Could I respond to that?
You can do that, but after all questions, in the end. Спасибо Вадиму. И следующий Савенков Геннадий. Савенков.
Спасибо, Бабу-Грине, за интересный доклад. Я хотел бы маленький просто комментарий к заявлению Анатолия Ивановича. Мы тут когда-то я показывал, Андреев показывал ядерный гамак Андреева. Дело в том, что железо и цинк, то есть нижняя точка склона. С левой стороны вот, во время синтеза идут реакции, ядерные реакции с потреблением энергии, а дальше уже идут с выделением энергии, а справа уже идут энергии с потреблением энергии. Потому, очевидно, идут обрывы на цинке, на железе. Второе, там, по поводу параллельных реакций. Длительность, скажем, одного акта отделения урана, это, значит, 7 наносекунд, 7 миллиардов долей секунды. То есть там реакции идут в масштабах ядерных. Поэтому то есть представление о том, что это все элементы появляются параллельно, это без учета того понимания того, что это ядерная реакция. Вот у меня все. Спасибо.
Спасибо. Немножко скомканно, Геннадий, но было понятно. Я думаю, что Боб Гринье понял, а уж Климов точно понял замечание. И это совершенно правильное, потому что вот эта кривая, о которой начал говорить Пархомов и про которую я прокомментировал, она имеет максимум на железе, на никеле. И действительно слева идут реакции с выделением синтеза, а справа идут реакции с поглощением. Но, Геннадий, вот я хочу вам сказать, вот вы можете это сами попробовать. Если на бумажке, вне зависимости от того, находится элемент слева от железа никеля или справа от железа никеля, если вы к нему, к ядру добавите протон, просто попробуйте по таблице, посчитайте, то вы увидите, что каждый раз будет выделяться энергия этого самого, энергия дефекта масс. Поэтому вот это вот представление о том, что где-то там что-то выделяется, а где-то что-то поглощается, оно не совсем точное. Спасибо Геннадию за комментарий. Владимир Бычков комментирует.
Thank you, Bob, for interesting presentation. But I want to say, as I usually say at such meetings, that during the last period we see the resemblance of studies in cold fusion with the situation in elementary particles. The more experiments are made, the further new questions appear, and the new questions do not answer the old questions. And this is connected with that fact, very sad fact, that nobody tries to understand this phenomena with new classical approaches. Everybody knows one quantum physics, another quantum electrodynamics, and everybody knows they don't work. They don't work correctly. And so each of the group tried to attach this or that theory without understanding from the basics of physics. So we see the situation became as in physics of elementary particles. Nobody knows what is going on, and nobody knows why it is so many elementary particles now. So here we see many new experiments, and nobody knows why it is they are going in that way which we are doing. Thank you.
Спасибо Владимиру Бычкову за комментарий. Это Bob, it's not last comment. I have comment, but may I do that comment after your response on previous comments? My comment will be finalizing. My comment will be not for your presentation, but about total situation connecting with the transmutation, not with your presentation. Bob, your response, and after that I finalize our today webinar.
Okay, thank you very much. Yeah, so on the subject of contamination, obviously that is something that you obviously need to consider. And in the case of the titanium here and the PTFE, these are samples that we can test, samples of the source material, and they do appear to be essentially pure materials. And when you look at the two subsets of experiments that we observed in this explosive event, you see these open nanocrystals formed, and on the nanocrystals you see these self-organized structures which are cones and rods, and they are built up from a toroidal viewpoint, a structure that starts with nickel at the base, iron, chrome, titanium, and then a carbon nanotube. And I'm saying that the source of the carbon is from the CF in the PTFE, and the source of the titanium in there is the titanium metal itself. And in fact, all you see are the elements which are alpha conjugate nuclei with basically the leftovers of carbon that the exotic vacuum object is carrying being dumped out as a carbon nanotube at the end. So as it kind of runs its payload out, it then leaves a carbon nanotube at the end. Conversely, when you are looking at the material, so if we look here, it's this area here is a piece of the PTFE that kind of moved from here to embed itself within this titanium oxide matrix here. And if we go into that structure, you have this piece here, which you can see, this is titanium oxide crystals over here. This is the piece of PTFE. And in the center of this section, like there's a radius around this piece of PTFE, which is kind of teleported into the center here, you have the plasmoid. And if we go in to look at that plasmoid much closer, you can see that the elements are, you then see fluorine, which is absolutely not present in the other part of the experiment, which I just showed you. And then you see alpha conjugate nuclei on the fluorine here, which are not present in the other things. And this is a plasmoid burrowing into the PTFE. So it's like consuming the carbon. Obviously, there's a lot of carbon because it's kind of leaving that behind. It has got some traces of the titanium and some iron in here, and it seems to be synthesizing some elements as well, which are not straight alpha conjugate nuclei, but it's doing something more interesting in here. And I think this is probably because it's got oxygen and protons from the start material. So I don't think that this can be readily explained by contamination, these two observations in this one experiment. And by the way, we might have just got lucky with this experiment. It took 4 hits between the titanium and the PTFE before we saw this explosive event. But I imagine if you had access to the Омасы gas, it wouldn't take you more than 20 minutes to an hour to repeat this or a similar observation. So I don't really think there's much to worry about in terms of contamination there. Then there is the coin, and granted, coins are very dirty, and you know, you wouldn't have said that a coin could ever be clear, but this, I believe, is a magnetohydrodynamic structure in the plasma, and it has all of the same structure that you see in other examples. And then on the side of that, you have again this same structure here, and then on the copper oxide, you see the oxygen being consumed, leaving the copper underneath, the more pure copper underneath. And these spheres, which contain sulfur, which is absolutely not present in any other place on this sample. It's only present on the on this side of this part of the structure in this overall magnetohydrodynamic structure. Then we come to the indium. The observations in indium here, where we have these plumes. And they are largely the rebirth of, you know, so firstly, there's nitrogen on the surface here. So nitrogen has, you've got indium nitride. This is possible to form, but this is because of the heating of the exposure of the indium to the gas, and it's absorbed nitrogen from the air because the experiment is done in air. However, the carbon here is extremely high compared to what one might imagine, but the actual shape of the structure, this blowing out of the structure here, is a near identical match to Takaaki Matsumoto's experiment. And bear in mind, I published these images before I'd even become aware of this work of Takaaki Matsumoto. So you know, I guess we could both be wrong, that's possible, but he's got lead and it's coming out of a pole. And this is, I believe, exactly what is going on when we are looking at this. And given the fact that these, where is it? This one. Given the fact that these experiments take such little time, you know, it took us 4 or 5 days to negotiate 2 hours of access to the gas. But given they take so little time, they're an experiment that could be replicated very, very readily, and you could choose the most pure material you could possibly find. But the observation of Matsumoto here, which is of the same order of scale, with the same kind of reducing whatever element is input to carbon, you know, that's what observed. Now, I want to speak to Alexander Parkhomov's point of view about, and I completely agree with it, and I you know, it's the same sort of thinking. Now I understand what was being asked of me by Anatoly Klimov, that you don't see above iron, and in the case of one of the other experiments, you can see just about some copper being produced in this plasmoid here. You can see just a bit of copper, and that might be because we have fluorine involved here. It can get to copper, okay, because it's odd, 63 and 65. Somehow it's getting to copper. But otherwise, we're only seeing up to nickel. And I believe that that's because there is a ready availability of carbon and protons. And so that when the plasmoid, the macro cluster that's doing all of its synthesis, is doing all of its synthesis, it's a bit like Leclerc is saying in 2012 or whatever, when he was making this presentation, that he says, if you you know, if you have more than 55% carbon, just the carbon, then you can't really go beyond iron. You know, iron is like the limit. And so it keeps fissioning back and fusing forward and fissioning back. So if you're doing this in an environment of 78% nitrogen and 21% oxygen in the air, you've got and moisture in the air, you've got a ready abundance of lower mass nuclei to work with. So you're never going to be able to get much beyond iron. But the cohering process has been shown in cavitation by Leclerc and by ourselves, by the way. We've been able to produce silver and other elements in cavitation. You can keep going up the table, but it is most of the elements are below iron. You have to kind of really push resonantly the same spot to force it up higher. And so I think it's the observations are entirely consistent with the claims by Mikhail Solin, by Ken Shoulders, by Takaaki Matsumoto, by Yul Brown. I mean, Yul Brown's patent clearly says that you can take radioactive material and when he exposes it to HHO, he is synthesizing mostly carbon, but elements that we typically observe. So he's saying here, you know, it converts nuclear and toxic waste to harmless carbon. So this is the observation, and anyone can repeat it, really.
Bob, you repeat your presentation once again in your response. Thank you very much. И позвольте я скажу тоже несколько слов по-русски. Ну, надеюсь, что Боб поймет с помощью переводчика. Я не буду говорить о существе доклада вот в части трансмутации элементов, а хочу обратить внимание немножко на другую сторону этого доклада. Это речь идет о том, что Боб Гринье связывает процессы трансмутации с формированием особой формы электромагнитного поля, солитонной формы электромагнитного поля, которые, ну, некоторые исследователи, вот, например, Кен Шолдерс и Климов, там и Шишкин, и некоторые другие, вот, наблюдают, и они, собственно, на этом основывают свои какие-то, ну, не столько теоретические, сколько, ну, некоторые пока еще предварительные объяснения того, что они наблюдают. Вот эти структуры электромагнитные, полевые такие образования. Я хочу обратить внимание, что все это очень напоминает ту ситуацию, которая сложилась в исследовании электромагнетизма в конце XIX и начале XX века. Я имею в виду спор между дискуссией, и там даже были более серьезные отношения, чем просто спор между Эдисоном и Теслой, и между, ну, по сути дела, в теоретическом плане, между Эйнштейном, между Лоренцем и Пуанкаре, там, и другими, теми, кто придерживался, ну, неполевых подходов в объяснении электромагнитных явлений. И вот мне, например, представляется то, что мы сейчас наблюдаем, очень похожей картиной, потому что есть люди, которые пытаются объяснять многие процессы путем образования особых форм вещества, то есть протонов, электронов, ну и, может быть, нейтронов, а есть люди, которые пытаются объяснять процессы, которые мы вот изучаем с помощью только электромагнитных построений, электромагнитных солитонов. И вот, ну, абсолютная аналогия, на мой взгляд, очень близкая аналогия вот того, что было буквально там 120 лет назад, и то, что мы сейчас наблюдаем в этом вопросе. Ну и я бы предположил, что можно допустить, что наконец-то где-то когда-то возникнет Эйнштейн номер 2, Эйнштейн в кавычках, вот в наше время, который скажет: нет никаких солитонов, нет никаких, значит, там атомных преобразований, ядерных преобразований, а есть просто какие-то особые изменения пространства и времени. Я такое допускаю, что приводит вот в результате к таким вот странным трансмутациям и там энергетическим преобразованиям. Хорошо, кстати, что Боб Гринье сегодня практически ни разу не говорил о том, что все это сопровождается энергетическими мощными процессами, то есть связанными с выделением энергии, но он этого не касался, он говорил в основном о трансмутациях. Друзья, мне тоже очень понравился этот доклад, я тут много нового для себя почерпнул. На этом мы эту презентацию заканчиваем. Спасибо Бобу Гринье. И о том, когда будет следующий вебинар и тему следующего вебинара, мы узнаем в следующее воскресенье. Спасибо всем. На этом я завершаю наш вебинар. Спасибо.
Спасибо.
Я